You have an optical transition, right? You can move electron from the field orbital to the empty one, right? As in gas solid, or within this partially filled band, that's in the case of metal, right? And the appearance, right? The visible appearance, why we call visible. The word visible means that we are in the spectrum, in the region of spectrum that our eye can pick up, which is the visible range. Okay, or depending on the degree of absorption and reflection in this visible region of the electromagnetic spectrum, which is typically the visible spectrum of, as you know, is around 300 to 800, roughly 350 to 760 nanometers, right? Remember the wavelength of our visible light that our eye can see. It corresponds to about in electron volt, because we like to think in terms of electron volt for electronic energy structure. It's about 1.5 to 3 electron volts. So that's a nice number to remember. 1.5 to 3 electron volt. That corresponds to this visible range that we see. So and the solid, if you have a solid with an energy band gap in this region, right? Then you can either absorb the light or reflect this light, right? Then you would give this material the color. Okay, so the material with this kind of band gap will give you yellow to deep red and red as the band gap move through this electronic structure. So 1.5, 1.5, and so forth. So gold and copper, for example, will have a region, right? We will be able to absorb something like 1.5 or something. That's what it will give it the appearance of this color, because it happens to have the band structure is such that you can absorb this radiation in this energy range, and it's special because it only happens to gold and copper in the entire periodic table that you see, right? The metallic part of the table. So it's a little bit special that way. However, if you have a band gap below 1.5 electron volt, right, which means that you are in the infrared region, right? And what do you see? The solid will appear dark in color, shiny metallic, and depending on the reflectivity that you have, which is what most metal is, because most metal has these happen to have gap that below 1.5 electron volt. And therefore, when you look at all the metal, from platinum, palladium, nickel, silver, they all look the same. They all look essentially dark, shiny, dark objects like this. However, if you have band gap greater than 3 electron volt in the ultraviolet, that means it would not absorb any light at all in the visible spectrum. And you basically have transparent material, right? Like zinc oxide, tin oxide has a band gap of 3.4 electron volt for zinc oxide. You look down, it's go through. It doesn't absorb any light except in the ultraviolet. So in the visible range for our eye, it's like glass. You just see right through. And that's known as the transparent conductive oxide, zinc oxide. A lot of quantum dot structures are like this as well, depending on the region. So, may scatter, sometimes light can scatter at defect, at crystalline site at grain boundaries, of course. So, if you have powder spectra, if you have little powder sample, it appears as white. Okay, so in this room, right, all the white paint that you see has titanium oxide powder inside, right? They mix titanium powder inside to scatter the light so that they appear white. Okay, this is how you generate white paint, and you will see them. However, so in the early days of cosmetic, when people go to the beach, they have suntan lotion, okay, and suntan lotion is material containing zinc oxide. So in the early days of cosmetic, when you put suntan lotion on the beach, what you see is that you see a white paste, right? And why is that? Well, because of this effect that when you make powder, in this scale, in the micron scale, it tends to scatter light, and there's a lot of defect within the zinc oxide scatter light, so you appear white paste. However, as time goes on, this is where nanotechnology comes about. People discover, well, maybe we can make the zinc oxide into nano powder, much smaller. Okay. Now, once they do make it much smaller, they carry a lot of the defect, and you don't see white paste anymore because it just go right through. There's no absorption in the visible spectrum, so transparent oxide become transparent again, right? Due to the lack of defect, because you make each powder so small. So this is nano powder. This is the first emergence of nanotechnology. It's good because making when you go to the beach, you don't have this unsightly white paste on your body as you try to protect yourself. Okay, so that's the origin of application of one of these. As you make things small, carries of grain defects, and then you make it behave like what it should. Instead of scattering, white scattering, you give it the white appearance. Okay, so I'm going to stop here. And I'll continue next day. Again, the assignment 2 is due on next Tuesday, and I'll try to post the solution in the next day or so. Okay.